happy time zone. What is going on with this? Oh my god. Hi, I'm in the center of the screen because I was just in a work meeting. Let's fix that. Boop. Now I'm over here. Alright, so we're gonna keep going with what Kiri was working on last time. She is forcing me to do this. I'm being subjected to an image format from 1987 that's documented like an image format from 1987. This doesn't make sense. So I discovered a few things already. I came in, swooped in, as it were, because I'm a burb. Get it? Burb. Yeah. Okay. All right. Let's position ourselves there. Yeah. So, we got this table, right? So it's a bit stream. I've come to terms with the fact that it is a bit stream, and we have this is like, okay, these are the binary bytes, and this is the codes that it's reading. And I just figured out what I was talking about, or what I was confused by. Awesome. Okay, cool. Oh, never mind. Actually, no, I'm still, yeah, okay. I was misreading this table. Anyway, we got, this is the 9-bit, this is an example is using 9-bit codes because it's a 256 color image. You know, back in the day, the thing that we thought we'd never get more realistic than this, 256 colors at a time. Oh my god, this is so much. Anyway, I was confused by this because we got this binary number. And it's actually read as like these bits, right? And I was reading it as like, okay, we got 8 bits and then a 1 and then a 1, right? And how does that turn into hex 100? The answer is it doesn't. That is not a thing that it does, because this goes onto this table, not this. This goes onto this table. The word wrapping does not wrap around like all the way over to here, because yeah, this table is just a little bit hard for me to read. It's, not very smart. Silence and we hear, make the sounds of the soundtrack to the rebellion. So yeah, neat, right? I was like, Loki, how can you be so freaking adorable? Anyway, so yeah, these 9 bits obviously turn into hex 100. That makes sense. We still need to, I think I'm reading the bits wrong here. So I did a little tiny bit of code off stream. I'm sorry. It's not AI generated, I swear. It's NHP generated. Hey, Mnemotic. Anyway, this code right here is wrong. We got this, like, we take the bytes. Also, I figured out that there is actually the minimum code size and then a block count. How are we today, Junk Raven? I am awake. I am being subjected to this code that Kiri wrote. But I'm okay. I'm okay. I was kind of tucked away there for a bit, but I'm back. Let me just say that, like, with a little bit less enthusiasm. I don't know. It's been rough. The soundtrack to the rebellion. Okay. So we get the bytes that correspond to the block count, and now the bit stream is just the bytes that we care about. And I just realized work. It works part of it. Let's just print this on new lines. Okay. So yeah, we are right now. What we're doing is we have 2 different versions of this, and I think they're both buggy. Where we are either reading from one end, from the highest bit, and going down to the lowest bit, or we are going up to Why are you biting me? Sheesh. Bites, just bites. No, it's bits. We're dealing with bits, not bites. Yeah, okay, so if blah blah blah, minimum code size, blah blah blah, so this is actually made complicated by the fact that we are doing like 4 bits at a time, I think, and I'm having a hard time kind of reconciling that with the actual bit ordering here. Okay, so we're reading from the end, and then we're putting that into a. So we're getting the most significant bit. Yeah, we're getting the most significant bit, and then we're pushing it over towards the first bit, right? Hello, Zofty. Actually, wait a minute. Ah, I did a dumb. No, I didn't. I did a smart thing. Yep. I'm a smart burb. So yeah, we're just trying to get the bits out of the thing, which, you know, this is the GIF that we're trying to decompress. No, wait, not this one. This is the GIF that we're trying to decompress. So we have color indexes 1, 0, 1, 0, right? That's what we're trying to get out of this. What we're probably gonna get is 1, 0 and then something weird, right? But we should still see 1, 0, and instead we're seeing 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0. Yeah, cool. So I think I'm probably just screwing this up a bit. Let's just look the hex for 12 and 92. Hang on a second. Actually, let's do this. Oops. Okay, so we got 0C and 5C. Let's see, right? 1292. 0C, 5C. So 0C and 5C. Oops. And that's going to turn into 0000. And then C in binary, hex C in binary is A, B, C. 12 in decimal, which is the 4 and 8 bits in binary. So the 1, 2, wait, 2, 4, 8. Okay, there we go. And the next one is 5C. So it's gonna be the that's 1 or 2 or wait no. That's 2 or wait no. 1 or 4, right? So we got 1 and 4, right? So this is what we should be seeing in our stream here. This makes no sense at all. Loki, you goober. Loki, don't touch the mic while I'm streaming. Come on. Look at this. Look at this goober. Obscured in disarray, how will they rose? This is now just a cat petting stream. So yeah, we got 0C, 5C. It looks like this. And those are the bytes. Those are the bits that we're getting out of it. We're getting 00001100, 00001100, and then 01010101, and then 11, which is actually well, yeah, that's correct actually. Sorry. Okay. How does this turn into 01000100? Now, in theory, the LZW minimum code size is 2. So we're actually reading codes like this. Okay, so this is actual image data. Compressed bytes. You also notice something interesting here in that the actual image data is smaller than the compressed bytes. This seems like an issue, but who am I to judge? Anyway, so yeah, the minimum LZW code size here is 2. According to, well, what we read from the file. At the crossroads of our fears. And according to this something, well, I guess the LZW minimum code size could also just be... What are we getting from the LZW minimum code size? We are getting 2, which is what we would get... LZW minimum code size is 2, block byte count is 2. So we're actually seeing, before any of this, we're actually seeing 1010, right? Hey, thank you so much for the raid, Evie. How's it going? Okay, so this is the LZW minimum code size, and then we have the block byte count, and then we have compressed bytes, which are, you know... Actually, hold on a second. These are decimal. Wait, no, hold on. They're not. These are... I'm just gonna say 2. Whatever. All lossless compression schemes have pathological cases that produce larger output than their input. Yeah, but the compressor would potentially be able to recognize the situation, or should be able to recognize this situation, and simply output an uncompressed one. Here's the thing: is like, I haven't read the compression algorithm exactly, but we're working on the GIF decoding, yeah. Because like in theory, and like if we just had this right here for the compressed bytes, that would actually work. Hello, Goth Zelda. How's it going? I believe, based on my knowledge of the decompression algorithm, that this would actually decompress to the correct thing. But we can't... I don't know what's going on here, because based on my knowledge of the decompression algorithm, this would be... This would make the first 2 pixels the same color, which they're obviously not. Right? Because these both exist in the, like, the decompression table. Now let's say we just like offset it by a bit. We end up with like this. Now this looks more correct. Right, just bear with me for a second here. Because this, what we have is we have the 0th color in the palette, and then we have the 1th color in the palette, which is not the first, don't get that confused. And then we have a thing that's past the end of the dictionary, which means that we do the LZW funky thing where we like add a thing to it, add something to the dictionary, all that stuff. We'd probably like redo the thing. However, The reason that this would also be wrong is because the first pixel is actually the second color in the palette. So we're actually looking for something that would be 0100. So this would also be incorrect. So how the hell do we get 0100 out of this? Is it like, do we start over here? This is also a potential case where, based on my loose understanding of the algorithm, where this could end up being like a different thing. Hey Lyra, how's it going? So yeah, I may also just be reading the compressed bytes completely incorrectly. Also a possibility. But it looks like that's 00001100, and then 1100. Cool. You're building a compression library. I am attempting to decompress a GIF. I'm attempting to decompress this GIF. Trying to keep it like as simple as possible. Hello Rick, how's it going? Burb was playing Armored Core. It's true. Yeah, I beat Armored Core 6. I got all 3 endings. It was pretty cool. Let's make an even smaller GIF. Let's make a 1x1 GIF. Image. Mode. Index. Generate an optimal palette of 4 colors. Sure. Export. Woof, don't look at that. Why did I go there? Weird. Oops. All right, so we're gonna load really tiny.gif instead of tiny.gif. Let's see what we get when there's a single byte. Oh, hold on. I forgot to actually hit the export button. We making GIFs? We are attempting to decode GIFs. Okay, so we got minimum code size 2, block byte count 2. Thank you so much for the follow, Axolot1. Well, it looks like Axolotl when you... Perio Pro has redeemed a...
You?
No, wait, hold on. Haven't had breakfast or anything yet.
You?
There we go. Alright, close enough. Oh, Eevee's a burb. Oh, okay. Oh, you were playing Armored Core. Okay. Eevee was playing Armored Core. Cool. How'd you like it? Which Armored Core? Sorry about that little misunderstanding. Anyway, why is this? Okay, so we got minimum code size 2. It's not interlaced. Doesn't have a local color table. It's 1x1 pixel. Minimum code size 2. Block byte count is 2. Weird. And then we get 0100 0100. That's so weird. I must be completely doing these wrong. Am I like off by 1? 68. What is 68 in hex? .68 in hex is 44. Should be 1, 2, 3. Maybe that. If we read in blocks of 2, we get that. That doesn't make any sense either. And again, we're getting minimum code size and block byte count is 2 and 2. If we go back to the Wikipedia page here, we will see that this is pretty much the same thing. We got start of image, LZW minimum code size, and then beginning of the first block specifying 11 bytes of encoded data to follow. So instead of that, we're getting... Oh, gotta hydrate, thank you. Actually, wait a minute. Is this GIF? Can I get a copy of that GIF? Sample image enlarged. What if it wasn't enlarged? Can we have a non-enlarged version? Large image of solid color. If I could get a copy of this GIF, then I could compare my stuff to the example here. I wonder if there's anything in the history here. I'm just trying to figure out if they actually had the image on there before it got enlarged. Oh, we're just searching through the same results over and over and over again. Crap. Oh, interesting. This one actually has the bits starting at the bottom? The least significant bits start at the... Oh, wait, hold on. Oh, wait a minute, hold on. Maybe I was actually right the first time I attempted this. It's actually going to start at the bottom, but we're still going to have the most significant bit of that part be the most significant. Oh my god, okay, this is going to be annoying. Freaking butts. Why are you like this? Why are we like this? Well, can you image search it? Maybe. I don't know. So we're going to be reading starting from the least significant bit and going to the most significant bit, but the way that we're actually writing it out right now has the number in the wrong order. So we'd be going from the least significant bit would end up in the highest slot. So we need to flip that around somehow. I'm trying to figure out how to do this in a clean way. a clean and normal way for normal people, because we're extremely normal here. Okay, so that'll start at the least significant bit and move up from there. And we'll start from the least significant bit and move to the highest significant bit. That'll also start that way. So we should have something more correct now, maybe, possibly, maybe a little bit. Well, we're getting a 0. We're getting a 0 for the first for the thing. So that's a good start. That's a good start. And then I think we might be getting the there's two. Okay. There's two special values that they give in the special fancy GIF version of LZW compression. There's a clear code, which is 2 to the power of code size. The code size indicated as 4, image is 4 bits per pixel. The clear code would be 16. Clear code can appear at any point in the image stream. Or image data stream, and therefore it requires the LZW algorithm to process succeeding codes as if new data was a stream, blah, 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 blah. End of information code is defined that explicitly indicates the end of the image stream. LZW processing terminates this when the code is encountered. The value of the code is clear code plus 1. Okay. So, we would have... Let's see, so the clear code would be 2 to the n. And if we have minimum, wait, hold on. This is be. How does it? But how do we read it if it's 2 to the n and n is it's the code size? What? I am now more confused than I was before, but I think we're also more correct than we were before. Let's go back to tiny.gif. Okay, in tiny.gif we got 0, which is wrong, and then we got 11, which is also wrong, and then this is all of this is wrong. This is terrible. What am I even doing with my life? We're gonna have to deal with this later on too, interlacing. That's gonna be fun. This Wikipedia article is just—it's actually like wrong in a bunch of spots too, so we can't really rely on it. Okay, so the first one. Wait, hold on. Wait, hold on. It gets a clear and then end. In this example, it gets like a. Oh wait, no, this is just the table. So the 9-bit code it gets is clear. The first one it gets is clear. That's not what we're getting for the first one, but sure, whatever. Actually, that might be. That might be... Is that the clear code right there? We're still getting like a 0 byte for the first thing, which is clearly incorrect. Like our very first byte shouldn't be 0. Our very first code should not be 0. Just straight up. Let's try something a little bit different. Let's go back to the icon.gif. A full one with like the whole ass. Okay. Minimum code size is 8, and the block byte count is 255. If we load up that image, file, open recent. Oh, we only needed like... Oh, wait, no. Icon.gif. There we go. Alright, behold. Icon.gif. So this has the entire, like... 255 range. It says the minimum code size is 8. However, we know from the spec that when it says 8, that really means 9. So I think we might actually... Do we have to add 1 to the minimum code size? Also, let's see what we got as far as, like... And the very first color code that we get is 157, which is kind of weird, but okay. What is 157 in binary? Is there a way to print binary stuff in Python? Python print binary. Okay. Is that it? Hey, there we go. Nice. And then what are we seeing here? We're seeing 1 1 1 1 oh. But yeah, so even like 111011100 versus that's incorrect. That is wrong. We're close, but we're definitely reading that number incorrectly. Also, I still don't know why the zeros are here. What is that? It's like an extra just byte of data that's just like... Is that the clear code? Oh! That is the clear code. Because if we do this, now we get... now we get the number, but it's reversed. Okay. Alright, I think we might be closing in on this. Right? We get... Sorry, not that one. Looking for 1 1 0 1 0 1 1 1 0 0 1 I guess with another 0 at the end of it because it's a 9-bit code for an 8-bit table. Which means that yeah, the numbers are reversed, so we have them in the wrong order. Which means that maybe we were right about this part. No, it's still wrong. Why can't I just read a binary number in the right order? Ah! This should be easy for me. This should be easy for me, but it's not, because yeah, just pain. So much pain. This is probably gonna be off by one still. Oh no, it's off by. Yeah, that's okay. That's not good. That's gonna be -1 from that. And then what we got? We got 1 0 1 1 1 1 0 1. Why are you still in the wrong order? Oh, I don't like this. We're only reading one bit at a time, so none of this ever... Oh, no. Okay. You got a new outfit? What? No, I didn't. I've been wearing the sports bra since... Well, you actually don't want to know how long I've been wearing the sports bra for. Okay, yeah, we're still reading stuff in the wrong order. How do we convert something to binary in Jodot? Is there like a format? Can we do this? Pretty please, pretty please. We cannot, no. Damn. It doesn't like formatting binary. We have to write a function to do this. Func, get binary string. C of type int, turn string. Var s equals blah, while c greater than 0, s equals s plus c and 1, c right shift 1. This will have the exact same issue where unless we do, it's gonna be stir, see, blah 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 blah. We gotta do this. Yeah. Okay. Turn S. Stir equal stir C blah 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 plus S. That'll be adding it to the other end. Okay, cool. Print get binary string bits. Actually, let's do this. Percent 5D. 5x rather. And then percent 8s. There we go. All right, look at that. That is producing some very haphazard looking numbers. Let's add a bits count. While len s less than bits count. S equals 0 plus s. So we'll just pad the start. LZW minimum code size in there, and what do we got? Okay, the numbers are inverted. Because I believe this is supposed to be that clear code. We're supposed to get a clear code first. So let's go ahead and find a way to flip this one around. Again, once more, guys. Or flip it back around. I don't know. Ah, we got it. We got the clear code. We got the clear code just like in the thing. Check it out. Hell yeah. Just like in the example here. That's the clear code. Sorry, that's the clear code right there. And then we actually get like color values. So let's see what those color values are. I want to print them out in decimal because I don't want to convert 9D into Alright, so our very first color value is 157. Hell yeah. Hell yeah. What is our very first color on here? Color index 157. We have read the first pixel of a GIF successfully. Hell yeah. Hell yeah. Sorry, I have to give a different kind of thumbs up after seeing a different movie. If you know, you know. If you don't spoil it for anyone. Let's see. It's a very good movie, though. Okay. Let's see if we can load our teeny image again. File dot to lower dot lazy ass Curie. Oh my god. Okay, we got that. We need to right, I was gonna try using the where's our there it is. The ready function needs to be moved up a little bit. Thank you so much for the follow, Lost Angel Dev. How's it going? There we go. Let's go back to tiny.gif and see if we can load that one up. Boop! We have failed. Out of bounds index 2 on base packed byte array. Okay. That's interesting. Oh, wait a minute. Right, that for loop needs to change. Hmm. But let's just see what we got printed out anyway. We got the clear code. We got 1, and then we got 0, which is actually correct for the teeny.gif. This one. This is index number 1, and this is an index number 0, right? 1, 0. And then we get something a little bit weird. We get an 11D, or a 6, if you read it in decimal, like a normal person. We get a 6, and I think that is... that is an indicate. That is something past. I don't think that's in the clear code. Wait. That's actually okay. So here's the clear code. Oh, geez. I just heard something thump against the house. I think another branch may have fallen down or something. It's really heckin' windy outside, by the way. Now I actually have to start getting onto the decoding. So the clear code is 100, and then we have the clear code +1, +2 are special values, right? A special clear code is defined which resets all compression decompression parameters in tables to a startup state. Value of this code is 2 to the power of code size. So code size is 2, which means that is 2 to the power of 2, which is 4, which is what we have right here. That's our clear code. There's an end of information code. Must be the last code output by the encoder for an image. The value of this code is clear code +1. And then we have the first available compression code is clear code +2. Clear code +2 is going to be it's going to be 100 binary +2, and this is going to be 4, right, and 2, which means the result is 110 in binary, which is 6. And that is actually what we are seeing right here. So this right here is the first value that we don't actually have in the table at startup. So when we started up, we have a dictionary or a table or something that is a mapping of every, like a 1-to-1 mapping of like every color code to like a color code. Every like LZW decompressed code value to a color code, like directly. So 1 means 1, 2 means 2, all that stuff. But then once you get past like once you get up to 255, the next one, 256, that's if you're looking at like an 8-bit one of these, like 256 color, right? So it'd be the max color value would be 255. 255 just means color value 255. 256 means the clear code. 257 means the end of data. And then 258 would mean the first value that's not in the starting dictionary. And that's when we have to start filling in the dictionary ourselves. Right? Can I get a sanity check on this, pretty please? Okay, so if we scroll down to decompressing, it's not in here. There's compression. Where's deferred clear code? What the hell? Because of a large base of decoders that do not handle the decompression in this manner, we ask GIF encoding software to not implement this feature until at least January 1991. Sorry, no sanity left? Okay, well, I was... So the end of... At least we're getting codes out of this thing, which is cool. So the end of data thing, that's gonna be... Oh, that's gonna be 101, right? It's gonna be this -1, so... that's the end of the data right there, which means that we have actually reached the end of the image, which is why it crashed, because it was trying to read after that, right? So yeah, we just have to now go and figure out the part of the algorithm that is reconstructing the dictionary, which is kind of the part that I was afraid of. I wasn't actually afraid of all the bit decoding stuff. I was afraid of this. And to do this, we have to start understanding LZW encoding a little bit better. Initialize the dictionary to contain all strings of length 1. Right, that's what I was talking about with the palette initially like filled, or the codes initially filled to match the palette directly. Read the next encoded symbol. If the symbol is not encoded in the dictionary, go to step 7. Okay, so that's the point that we're at right now. The symbol is not in the dictionary, it's past the end of it. Concatenate the previous string emitted to the output with its first symbol. Call this string V. Its first symbol. Add V to the dictionary and emit V to output. Okay, let's actually go back to the very beginning of this, because we have our codes, right? We have is the clear code actually included in this? Wait, do we consider the clear code separately from the compression algorithm, or can the clear code actually end up as part of the decompression? So, that's gonna be confused. That would be really weird. Hold on a second. There's a little bit of ambiguity here, and I don't like that. Anyway, let's go ahead and let's assume that we're not going to use it. So, initialize the dictionary to contain all strings of length 1. Read the next encoded symbol. So the next encoded symbol is going to be, it's going to be 1, right? This symbol is not encoded in the dictionary, go to step 7. It is, because it's one of the ones that directly maps, right? Emit the corresponding string W to output. Yeah, that's the decoded thing. So it's the 1 value directly. We emit 1 to the output. Concatenate the previous string emitted to the output with the first symbol of W. Concatenate the previous string emitted to the output with the first symbol of W. Add this to the dictionary. The output with the first symbol of W. Concatenate the previous string emitted to the output. There is no previous string. We're not going to add anything yet. But let's build up our sort of like little hypothetical here in the image that we have, right? Because we actually have this data right here. Okay, so we're gonna say that is in the dictionary for the purposes of this. Is in the dictionary, output the value. So we're gonna keep track of a sort of like last value and current, I guess. So we're gonna say we'll do this differently. We'll do this with a whole ass table. last, current. This would be easier to do in Emacs, though. Thanks so much for the follow, Madam Musel. How's it going? Alright, you know things are serious because I'm busting out org mode. Yep. Oops. And bam. That is... Crap, I screwed that up. There we go. Nope, still screwed that up. There we go. We don't actually have to worry about those first two columns anyway. So yeah, last is just 20. Current is 100. Because we read the 100 out there. So in this one, last is 100 and current is level 1. And then in this one, it's going to be... Last is going to be 001, and current is going to be 000. And then here... Hold on a second, I think it's a little bit... so here's the first one that we get that's not in the table. So we're going to take the last and the current, right? Concatenate the previous string emitted to the output with the first symbol of W. Wait, hold on. If the symbol is not encoded, okay, emit the corresponding string W to output. Okay, I'm confused, because what's the corresponding string W if there's no... If the thing isn't in the dictionary? All right, time to look up a different guide. Crap. All right, this is one of the ones that we were all looking at yesterday. New equals next input code. If new is not in the string table, S equals translation of old. S equals S plus C. Where's C? What the fuck? What is C? C is the old? No, wait. Old equals first input. What? Wait. Oh, this is so confusing. Why? Why can't fancy compression algorithms just be simple, you know? Oh, these are using ASCII values. So 65 and 66 are... I think those are the ASCII values for A and B, right? Yeah, that's just A and B. Okay. That was a little bit confusing. Okay, so old is 65, new is 66. And I get... S equals first character of S. S equals S plus C. we'll just keep track of a... Or is C current? Is that... Equals first character of S. Is the first character of the last thing that we output? Alright, we'll use the variable names from here. We'll get old, new, old, new. Just gonna do this empty too. Boop. Old is first input code. Okay, so first input code. And then new is next input code, which would be... Let's do this. New would be next input 100, would be next input code, and then we get not in the translation table, which it is, it's fine. So S is going to be translation of new. Alright, let's do this. Yeah, new is that, and that's just going to translate to 1. And then... Wait, hold on. Oh, no! That's actually going to be the clear code. We don't actually... When we read in a new value... We're actually dealing with just the old value stuff. New is not in the string table. S equals translation of new. Okay, so we also have, yeah, so translation of new is that. Okay. And we output S. Okay, there's our table as it exists right now. So next one we're going to get is, so I guess old, let's see, old equals new. So old equals new. We're going to say that's that. And then the next one we're going to get is going to be old plus C to the string table. C equals first character of S. Wait, hold on. There's the output S. C equals first character of S. C equals first character of S. It's gonna be clear. Old plus C gets added to the string table, so old plus C. Old plus there is no C yet. Wait, C is the first character of S. So we're gonna add. Wait, old plus C. That doesn't make sense because that's not even old plus C. Old is just old is what are we gonna add? Like we're gonna add like the clear meaning plus. It's not doing a good job of distinguishing between the decoded values and the encoded values here. Aw, heck. Thanks. Let's go back to that Wikipedia article and see what it says. Because they had an example of the decoding, right? Get the clear. First pixel always output string found in table. Always add first string to table. Initialize local string. So this is adding a string to the table. The string is going to be 28ff. 28ff. And we add a pair of those to the table. String. What is the weird spacing here? Ah! we know what we're supposed to get out of this, which is... Can we work backwards from this, maybe? Like, what we expect at the end of all this is going to be, I think right here. Clear, and it's going to be... That's going to be our output at the end of this, right? So, I'm going to make this a little bit smaller. I feel like maybe I need to split this up into a little bit finer grain stuff instead of... We can just try to implement this and see what happens, I guess. Hold plus C to the string table. Doesn't make any sense, because it's an input code, but it's not the actual string, right? Like, that doesn't make any sense. When is getting scary here? Yeah, here too. Hang on, I gotta be right back. Give me a minute. Alright, I am back. Ugh. Oh, hey, there's C++ code. That's actually much more convenient. Okay, so this is the dictionary that initializes. That's pretty easy to do. Old equals... Excuse me? That is... It's syntactically valid, but but... Was someone high when they wrote this? Why the... Where's this in even, like, declared? It says it compiles. I'm just. Oh, right. Yeah, no, that's it's declaring. Yeah, okay. That's just. I forgot my order of operations, but they shouldn't have written the code in a way that made it confusing about the order of operations. OG's Geeks for Geeks. Is there something I should be aware of with this? All right, yeah. So I'm gonna fix this code. Who would write C++ code like this? Are they just trying to torture me? Oh, it's pre-AI. Oh, that's lovely. Okay. No, it compiles without warnings, too. Neat. Actually, wait a minute. We should quickly scan this for any exploits or vulnerabilities before I run on my machine. Yep, no, it looks good. Looks good. No files getting opened or anything like that. And there we go. Okay. So this syntax right here, it's declaring the old and in values, but it's initializing the old value to a thing. However, you can also do things. Unfortunately, I think this is also valid syntax, and if you except that in isn't like declared, and I think if you did that, I would hate you forever. Let's actually. This is like it's in that realm of like people don't really understand this because nobody does it that way. Like there's a lot of conventions in C that like you just have to follow the conventions and you'll be fine. If you start doing weird stuff, everyone's gonna hate you. Int foo equals. I think you can do that, right? That's valid syntax. It generates a warning, but yeah, you can do that. Yeah, the comma operator in C and C++ is really funky. This is pointless, and you would never do it. Yeah, because one of these values would just get ignored, right? So when I saw this, I was like, "What's going on here?" You can also the thing is you can also declare like int x y, right? And then it declares x and y. So the question is like, what happens when you stick an equals right there? It's like depending on the operator precedence of comma versus equals, and nobody like in this context you don't usually think about the precedence of operator like comma versus equals. It makes sense because if you think about like a function call or something, foo x equals 1 bar, right? Then obviously this isn't the equivalent of this, right? It's just that like this you use all the time. Well, some of us use all the time. Where this is that you don't really see that pattern like that a lot. So I'll go back and fix up the code to be a little bit less annoying. Let's see. C++ code takes forever to compile. You know how long this takes to compile one file? Jeez. Okay, so init table. Is it 1 or 2? I think it's. I can't actually remember. I think it's the last one in the list. I think. Let's find out. Yeah, it's the last one in the list. Yeah, having like the comma thing inside of an expression usually kind of a little bit weird. Don't use commas and expressions in C, please. I mean, you know, unless it's like something like a argument list or something of a function call. That's obviously part of an expression that has comments in it. It's fine. But like the comma operator really shouldn't be a thing. Yeah, it kind of should have been a compiler error. Yep, I agree with that. There's a lot of things in C++ that I would change, actually, now that you mention it. Yeah, well, I don't get to make those decisions, unfortunately. Okay. Let's get next code. Is it in the dictionary? So C starts with this S0. That's interesting. Oh! Okay, hold on a second. There's our first value for C. Sounds cursed. Yeah, it's pretty cursed. Yeah, don't please. Look. You know what? It's already cursed enough that we do this stuff. This right here. Like the operator overloading of the left shift operator for like streams and stuff. Yeah. That's just how you print. No. Look, hold on. Here, let me show you a thing. It's called printf. We have C out at home. It's called printf. Want to see the whole of it? This is what this code. This is some code. I haven't written this code. This is code that I'm annotating because this is some LZW decompression code, which seems pretty simple on the, you know. C++ now has std print. Good. It's. I want to find it now. Temple class args, blah 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 blah. It's this is what it should have been all along. It should have been a var args thing that just yeah, it should have been like a var args thing that just takes whatever stuff you feed it and just I don't know. Look, I'm kind of done learning new C++ tricks. I'm learning Rust now. The way var args works in C is cursed too. Yeah, it's not. It's kind of gross. Variadic templates in C++, though, that is something that you can use to lose your mind if you want to. And this actually is a variadic template. So, you know, have fun with that. I mean, honestly, I would prefer implementing stuff using C var args over like variadic templates kind of any day. Just being on the implementation side of that. I mean, obviously this is convenient to use because you just say print and then you feed it whatever, and it just takes it, right? Just count. Okay.
Does it piss you off when I sound like this? Your anger makes it all worth it.
Hardcore team
Mixed mode manager? I think I might stay away from that. Nice one character variable names. What's S and C meant to be? I don't know, but this isn't actually an issue with this code. This is actually an issue with the like it's an issue in the original pseudocode also. But notice that the pseudocode doesn't actually initialize C to anything, which is really obnoxious. Anyway, old plus C to the string table. That's the part that I was confused about in here. So let's see what it does in C. Table old plus C. Ah, okay. That's not old. That's what you get when you look up old in the table. Because this looked like it was concatenating the code with the value from the table, which was like, that doesn't make any sense. This makes sense. That's, yeah. Anyway, S is, I believe, the current string, and C is something. C is just the current input character or output character. C is it's a character. It's not the cleanest pseudocode. No, it really is not. Thankfully, we have some C++ code here, which is something that I don't think I would ever usually say. But at least this stuff has to be syntactically like valid, you know. What's a little bit at the end here? Is that's a inverted percent sign. That's, I think this code might not be. Hang on a second. Valgrind powers activate. Fatal error. A function redirection which is mandatory for the platform. What? We'll compile it with a different compiler. Valgrind! Valgrind, no, I need you! Oh no! Install glibc's debug info package on this machine. I can't use Valgrind. This is bad. What are you coding LZW compression for? I'm coding LZW decompression, or attempting to anyway. It is so that we can decode GIFs. Yep, it's for the GIFs. Anyway, we're doing it in GDScript. We're actually just using the C++ code as a reference. That'd do it, yeah. Alright, I think we're gonna store the dictionary as like a thing on this object, like a global thing. Var current dictionary. So type. Thankfully we can just use a dictionary. Current, I guess, decoding table. And then we'll say func reset table. Max code size. Let's clear that out, and then we'll go through in range 0 through 1 left shifted to max code size. Current. Okay. Can show Twitch GIF avatars. That's my plan too. Because we have the overlays. So if you like spam emotes here, then they show up in the little like thing here. Ignore the ones that are floating, just the ones that are bouncing around. Unfortunately, it doesn't work for animated GIFs because it does not animate. It can't load animated GIFs from Twitch for it. So I want to fix that. And then once I'm done with that, I'm going to write an LBM and a PCX loader, all in GDScript. And then we're gonna release a retro format loader like thing on the asset store if I can get away with it. Asset library, the asset thing. It's gonna be free. It's not. I say store, but it's gonna be free. TGA loader. I think TGAs might already work. TGAs are like really simple anyway. You could just write your own loader for it. Let's actually see if TGAs work. Oh, yeah, we can just read the documentation. TGA. Load TGA from buffer. Yeah, we do not need to make a TGA loader for Jodot. Like TGA is this like really simplistic format. For anyone unfamiliar with TGA, TGA is a really simplistic format that has like the most just basic RLE compression in it. And it's used a lot in video games because anytime someone's writing their own engine and they don't want to deal with like image format crap, they just write a TGA loader because it's super simple. Are people still using it? Almost certainly. TGA is like the go-to image format when you just like, yeah, when you just, especially if you have like an engine where you're not even using like that image format at runtime. You're taking that image data and you're converting it into something like DXT or well BC compressed whatever stuff. It's named random old format from memory. Yeah, no, TGA is like super common. I imagine these days for like really big engines, they always have like, you know, the format decoders in them and stuff. But if you're writing your own engine and you don't want to deal with like the libraries and stuff for that, just write a TGA decoder. Here, I have my own TGA decoder already that I've written. There, that's my TGA loader. I don't know if this one actually does RLE. This loader only works with true color images and grayscale right now. RLE and non-RLE are okay, though. Yeah, there are a few formats that it doesn't work for, but those are the formats that we don't use anyway, so whatever. But it does do RLE compression. Write a TIFF decoder. Look, I wrote an LBM decoder, all right? I've stared into the void. LBM comes in like multiple flavors depending on if it was saved on an old PC or an Amiga. And it's like an IFF like container format thing, and yeah, it was just. Let me see if I have that stored anywhere. Yeah, it's in my DOS game repo somewhere. Let me go digging around my hard drive. That's the VGA code. It's not in there. Nope, also not there. Actually, wait a minute. There should be an LBM loader. There's an lbm.obj file. That's weird. Found it. All right, this is my LBM to GIF converter. I actually wrote a tool that would convert LBMs to GIFs. Had a very, very, very specific use case. Yeah, here we go. So to load an LBM file, you must... first of all, it stores things in big endian, I think. Let's see. LBM file read next chunk. Stores stuff in chunks. Merge bitplanes. We get to deal with bitplanes. Yeah, I love bitplanes. No, I don't. Let's see, LBM load buffer, check the format, read internal chunks, blah, 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 blah. Use the bitmap header, transparent colors, and you can actually save the lasso tool like selection in LBM files, which is kind of interesting. And then you can also store color cycling data inside of LBMs. There's two different ways of storing color cycling data. That are like different formatted blocks. Let me get the actual image data. For PBMs, the image data is stored interleaved instead of planes. We still have to deal with compression the same way. Also, some PBMs seem to stick a 0 in the plane count field. Neat! Add another plane for the mask if it exists. Pad row byte count up to 2 multiples. These were whole 16-bit words on the Amiga, I guess, maybe. We must have a BMHD already by the time we see a body. Oh yeah, look at this! I'm using GoTo. Look, this is a legitimate use of GoTo, okay? If this were Rust, I would just return a fail result. Also, I'm actually checking my malloc results here, which is kind of fun. You got to do that on when your address space is teeny tiny. All of these go-tos just go to this like fail down at the bottom, which just cleans up memory and continues. Oh, here we go for the RLE encoding. At least you're not using set jump long jump. So about that, my scripting engine, yeah, here's the fail. My scripting engine actually uses set jump and long jump for error handling. And you know what? Until I learned about like Rust style, like, you know, result enums and stuff, I figured that was probably the cleanest way to handle stuff. I'm still kind of like on the fence about it. Basically, Ninkasi, the scripting engine, has an interesting problem where it can have it's designed to be embedded as a library, and while embedded as a library, it is in C. Yeah, while it's embedded, it runs in DOS also. DOS, Windows, Linux. Even tested it on like PowerPC Linux, but anyway, has an interesting thing where, like, while embedded as a library, what can happen is you can have a hosting application will call Ninkasi and tell it to tick the interpreter. The interpreter can call a callback into the hosting application, and then that callback in the hosting application can end up calling more Ninkasi code. And so I want to be able to do a long jump to return an error from my Ninkasi code. And so what I have to do is I have to long jump over all the Ninkasi code back to the point that the call happens, the call back into Ninkasi, and then it returns to the hosting application. It errors out inside of its callback. It does whatever error handling stuff it wants to do there, and then it has to return into the Ninkasi interpreter, which then notices that it's in an error state and long jumps all the way back to the original like call site for the tick. It gets pretty nasty, yeah. Though if you read, okay, if you read the code for it, I think it makes sense why I did it. It's been a while though, but I think the set jump, long jump error handling is only for a specific circumstance. Also, it's the circumstance that I referred to as a catastrophic error. Let's see. Interestingly, for the preprocessor that I wrote for it, it doesn't actually use any of that. Yeah, there are two places where I use long jump. And basically it's all kind of wrapped up in this error handling macro stuff. So yeah, this is the catastrophic failure handler trigger. So this is the case where it's like something has happened so bad that we can no longer guarantee that the VM is in any kind of valid state. It is in a valid enough state that it can still be cleaned up without leaking anything. But we have to set like this flag to indicate that like do not attempt to run anything in this. The only time that we actually call this, well, let me see, NK save, that's for the serialization system. NK table.
Yeah, I'm falling in love with the corporate illustration.
Yeah, so there's you see comments like this. Here's something really important to note: because of the allocation failure long jump, this assignment will never complete in the case of a realloc failure. In fact, it won't even deallocate the old array. If this NKI realloc array call fails, then the table and the recorded capacity will remain unchanged. This is important because it means that the object and string table contents and ranges will remain sane in case of catastrophic fail, allowing save VM and external data cleanup. Safe VM and external cleanup. Crap. So yeah, where is NK catastrophe actually used? Let's find out. So it's used in like two files. It's used in NK mem in quite a few places, and that it is entirely limited to handling cases of allocation failures, because the alternative is to check the return value of every single malloc call, which is arguably a little bit worse. This is like that callback, like pass-through stuff that I was talking about. So if it notices there's been a catastrophe, then it will like go up the stack to the next like call point and stuff. So yeah, this is basically the wrapper around like. Also, look at this error string building. Oh my god. This is the wrapper around like calls into C functions, into opcode call. Yeah, the opcode call does a lot of stuff, unfortunately, because it can call internal functions, which are just like, you know, jumping to a different spot in the VM, pushing the code pointer, all that stuff, and pushing the current context. But this one is This is the C function callback happens right here. And I think this also... Yeah, this is just a debug function. But yeah, here's the other macros that go along with this. We have this set failure recovery and clear failure recovery. This is the part that actually does the set jump. And so it does the set jump. It calls into the VM. Maybe it has to hit a long jump to get out of that, and then we have and then if that actually triggers, if that actually triggers, then it'll return from this function, I think. Yeah. Set failure recovery, and it will return whatever X is. So we're giving it like a default value to return there. So when we say, like, you know, nkx value to float, X is for the external interface. Nkx value to float, we give it a, like a, basically a 0 to return on failure. And then clear failure recovery is... Yeah, and actually here's the actual set jump calls too, right in the macro. There's not too many layers of macro here, thankfully. So the other thing that it has also is this this stack of like set jump, long jump frames. So that again, it can do that thing where it like unwinds. It long jumps across its own code, but unwinds normally across like the hosting application's code. Anyway. Again, had I known about, like, you know, Rust's, the way that Rust handles errors with, like, result enums and all that stuff, I might have implemented this a little bit differently. But it is what it is. And honestly, if I ever implement Ninkasi in Rust for some weird reason, it's gonna be structured a lot differently. Ninkasi was a really fun project. I'm really proud of it. No one uses it, but I'm really proud of it. We were implementing LZW decompression, weren't we? Yeah, that's what we were doing. We got a thing to clear the dictionary, reset the entire table. So we're just gonna print out the entire current decoding table. Guess we're actually gonna do that right at the beginning, aren't we? Oh, we don't actually know how many bytes are gonna go into it yet. We need to know the minimum code size first. So that's gonna be down here. I think it's gotta be -1 for that. Oh, that's a normal error. Okay. Color table 0, 1, 2, 3. That is not correct. Wait, no, that is correct. Wait. Yeah, that's correct. I'm sorry, Mnemonic. I'm sorry my code is traumatizing you. Okay, let's see, lar decoding table position. Just gonna set that to 1? No. Int 1. Nope, 0. Such jump and long jump scare me. Truly cursed functions. Yeah. Yeah, they're pretty cursed. It's gonna be max code size +2. Decoding position, table position is set to 6. That is actually the first value that we get, which is correct. Nice. Excuse me. Okay, so we've reset the table, and everything should be initialized now. Which means that we should just be able to start reading bytes from the thing, right? Or does this still feel off? Let's just implement it the same way that it exists here. So let's just clear that out. Var C equals this var old. It's gonna be get bits LZW minimum code size. Int what does in do again? I can't remember. Let's actually replace in with next, because that sounds nicer. Let's call it next code, actually. Let's be really verbose. Old code and next code. Code. Let's run it. Looks good. Old code. Next code. Actually, wait a minute. Do we even need to next code? We don't even need to like declare that outside of the loop. So whatever. String S var S. No, that's not of type string. That's of type packed byte array. $C, which is also type packed byte array. Is that actually what we want to do? Or maybe we need to, oh, maybe we want to do array. This is, if I say packed byte array, then that's assuming that we're, you know what, we'll just do array. Array of int. Thank you for adding depth to the stream. Ow, wow, ow, ow, ow! There we go. That's a little bit better. So S actually starts off as current decoding table, old code. Let's me check that old code is in current decoding table. Ooh, error. One. C is initialized to the 0th index from the table. Okay, so we're actually going to do that. Do we actually even need to use a dictionary for this, or could we just use an array? We could just use an array. Already keeping track of the end of the table. Yeah, okay. And then we just got to do a for loop. What is op.size? Op.size. Oh, that's the codes. So now we're on our own for reading the actual codes. Right, so our got EOD is false. While not got EOD. Actually, we could just do while true and break when we get the EOD, I guess. Yeah, we'll just do while true. What's the worst that can happen if we do a while true, right? Nothing bad has ever happened as a result of saying while true. Let's see. Let's actually keep track of what the EOD code is. Var EOD code index equals 1, blah, 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 blah. Is leave W minimum code size is 1 plus 2. Wait, plus 1. And this is going to be clear code index, which are bookends. Okay, if next code equals EOD code index, then we are going to break. And we should be able to run this without it looping forever now. Out of bounds, index 4, in on base dictionary. It's the clear code though.
It's time for your next adventure. I have no idea what I'm going to do tomorrow. How exciting.
Do while 0 is valid in C. Yeah, that's actually a really, really handy thing also. Works great with them. It's a way to work around some like macro, some weirdness between like the interaction of if syntax and macros, and semicolons. Trying to think of how to do this. What does that clear code do again? Clear code can appear anytime, requires the LZW algorithm to process succeeding codes as if a new data stream was starting. Encoders should output a clear code. It's the first code of each image data stream. I guess we could just have that in the dictionary, couldn't we? I mean, it's like those indexes aren't going to be used anyway, right? So... So if the new data stream is starting. Oh, wait a minute. We should decode all the codes first into an array. Yeah, we should do that. We should do that. Okay. Yeah, we should do that. That way, I just leveled up. Nice. Okay, we're not gonna use that. We need to clear, like, get the codes into an array first. Okay. So while through, do this first. Next code equals blah 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 blah. Var codes. We actually want like an array of arrays. Is that right? No, that's not right. No, we do want an array of arrays. Yeah, we want an array of arrays. We want like an array int, which I don't think we can actually syntactically say. Yeah, no, that's not allowed. We're just gonna say array then. It's an array of So we're gonna keep, yeah, okay. Var codes. We'll do this. If next code equals blah 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 blah. Get bits. I'm imagining like splitting the. Okay. Splitting all of the. Splitting the codes into like multiple substreams. Codes codes -1 dot append next code. Is it append or add? Elif next code equals clear code index. Codes dot append empty array. Else. Okay. Okay. So we got array of arrays of substrings. Done getting codes entirely. Move to the next substring. Append this to the current substring. And at the end of this, we're just going to print codes. This will be all the codes in the file. And we're going to return because I'm a coward and I don't want to actually do proper error handling there. That is if okay, there we go. We have like a substream now that goes 106. So that's not including the clear code at the start. It's not including the EOD at the end. That is just image data. So now when we want to get the next now when we want to get the next index out of it, we'll do this for code list in codes. And then we can just do, I guess we could just do like a, we just do a for loop like this one, but it can be a for each loop for us. Trailing empty arrays. Okay. And then, yeah, we can make this a for code in code list. Except we're not doing. Oh, dang it, we're not doing that because we already. We need like an array slice. Mm. Yeah, I think we can just use next code there. We're deviating from that algorithm pretty far. Just like, you know, syntactically and stuff. Next code, blah 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 blah. Where's next code actually used in this? Next code. Yeah, okay, so that could be that's fine there. We're gonna ignore that because we don't need to handle that case there anymore. Now all we gotta do is handle table find. So if current decoding table dot has next code, that's going to be the equivalent of this. Let's see, s equals table next code. S equals else we're doing this. S equals table old code, S equals S plus C, S equals old code, S equals S plus C. That. And then we're going to clear out C. Oh, C just equals S0? I think that's equivalent. It's going to be amazing, absolutely amazing if this actually works on the first try. I have a lot of doubts. Table count equals table old plus... Just doing this. We're just going to do that. We're just going to copy that directly in because I've changed the code up enough that... This is actually bad. We are gonna have arrays like all over the place, like arrays of arrays of arrays of arrays, because of the way I set this up. Because it was using string concatenation in one way, and I'm using stuff in a different way. Actually, I think it's just gonna throw an error now that I think of it. There is an easy fix for that, though. No, there isn't. Actually, there's no easy fix for that. It's because I made the dictionary of... Okay, the dictionary needs to not be... Yeah, the dictionary isn't just of ints, it's actually of arrays. So now that we've done that, we have to go through and find all the... like this, get rid of that. Get rid of this. We don't need count, I think. Do we need count? No, wait. And that's not a packed byte array anymore, that's just an array. It's gonna be in like an array of packed byte arrays, but whatever. Well, it's gonna be an array of arrays, actually. Value of type int cannot be assigned to a variable of type array. Jeez. Okay. And invalid operands are array. Blah 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 blah. Position. And then old code is next code, and then we're done. Let's see if this actually runs like at all, and then we'll add the debug output. Nope, it doesn't. Trying to assign a value of type array to a value of type array int. Whatever, it's just an array then. We're throwing out the type safety because I don't care anymore. That doesn't make sense. What is current bitstream contents? It's an array of ints. Why? Oh wait, no. Wait, hold on. No, that doesn't make sense. No, wait. No, that doesn't make sense. That's actually that is not. Wait, current bitstream contents. Where the frick is current bitstream contents? That's not the value that we should be using at all. We should be using current. Oh my god. Okay. Maybe variable names can be too verbose. Weird. Out of bounds get index 6 on base dictionary. Yeah, I know, that's why I'm assigning something to. Okay, well it ran without any issues, so that's cool. Where's the part where we actually output stuff? That's right here, right? Let's just do print s. And we got 0, 1, 0. That's not right. It ain't right. Nope. Got 0, 1, 0, and yeah. A little county was table old code. Looks like we're making a new entry regardless of like this. So I don't know if we don't need to make a new entry to we just say S equals old code plus C. Okay, so let's walk through this because we have 106. So the first code that we're getting is a 1. Wait, what? Wait, why aren't we? We should be putting out a 1. Is this the LZW part? Yeah, it's the LZW decoding. We should actually be getting a 1 for the first thing here. Print got direct thing S. Got direct thing 0. Wait, it's because old code is the first. Oh, shoot. Oh, wait a minute. We actually needed output up here.
All flags secured. Maintain current posture.
Golden lights like the rain as I fall into the creek. Went into the water just to see if I sink. The taxi road.
Okay, this should go. So we got the for loop result is 1. Then we got result 0, and then we got result 1 0. That's actually correct. That's good. We got 1 0 1 0. Right. So 1 0 1 0. Oof. Oh yeah, between the like the code list thing also, we need to reset the entire table in between. So every time we get a new code list, I'm gonna do that. I think this should still behave the same. Yeah, good. And decompression results. I think there's like a special case in the GIFs also that we need to handle. Well, it's like a guess. Yeah, there's a special case in here somewhere. We have to. I'm just gonna put fix me. There's a special GIF case that we aren't handling yet. All right, and we got 1 0 1 0. Okay, nice, awesome, we got it. Let's see if that works with our other tiny GIF before we start moving up to bigger ones. That is a failure. That is a miserable, pathetic, horrible failure. Dang. So what happened here? We ran out of bits. We ran out of bits while we were doing the thing. Uh, true. It looks like we didn't get the end of stream indicator, or oh, we may have calculated the end of code index incorrectly. Right, let's see what codes we go. Identifier code, next code, next code. Okay, so we got blah 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 blah. We got a 0 at the end of that. That's not right. I think we've got to be like miscalculating the LZW minimum code size, because none of these look like they're end codes. So like, oh, please tell me it's not. We have this little +1 here. I'm kind of afraid. Yeah, that's great. That's cool. We're definitely not calculating the minimum code size correctly. Let's see. As described in Appendix F. Okay. This is... Right. So we're getting that out of there correctly. Appendix F. First byte of the compressed data stream is value indicating the minimum number of bits required to represent the set of actual pixels. Normally this would be the same as the number of color of bits. Because of some algorithmic constraints, however, black and white images which have one color bit must be indicated as having a code size of 2. Code size value also implies that the compression codes must start out 1 bit longer. Okay, I think we'll do this. If LZW minimum code size equals 1, LZW minimum code size equals 2. There's a weird exception in this stuff. It's probably not weird, but like... Okay, well there we go. That is, it's not face planting anymore. Which is tiny2.gif. That's definitely like not the correct decoding result though. And that's also incorrect because now we're not getting anything out of it. Yeah, I've just broken the decompression stuff, so that's cool. What was I doing before writing up that exception and then messing around with these like offsets? Alright, this still worked, right? Nope. Okay, this works. So we're back to the functioning version of it. We got 0, 1, 0. Okay. And let's just add our exception right in here. So it's going to be that, and then if LZW minimum code size equals 1, then LZW minimum code size equals 2. So this should... Why? What?
Some freak potential, but that's just great. It makes us.
How much does Artemis charge to program? I need a programmer. I earn like a salary at a game studio. I don't do like freelance coding stuff. Sorry. Okay, so we got minimum code size. Oh, minimum code size is 3. Interesting. Works with minimum code size 3. What is... So we're actually reading minimum code size 2, and we have to add 1 to that. So we're reading 2 from the file, and we're changing it to be 3. Stupid off by 1 nonsense. Oh my god, I'm using it in so many places now. Butts. We'll just okay, that still decodes correctly. Cool. And if we switch to tiny2.gif, then we fail. This is the part where we probably have to add the weird exception, right? Oh, wait, hold on. Clear code is that, EOD is that. 4 would be the clear code, that looks correct. Yeah, we're still not getting the EOD code. The EOD code is... That's the one we're getting right now, that's the one that's failing on. But the EOD code index is 5, when it should actually be 3. Clear code value would be 16. Clear code plus 1. That's weird. I don't know what's going on here. Okay, so the EOD code is clear code +1. So we could actually just say we can make this a lot simpler. That's not going to solve our bug though. The clear code that we get is 4, which means the EOD code would be 5, but now we're like... It's like there's out of bounds index, current bitstream byte, stream contents. Should we just like try padding with this with zeros? Let's try padding it with zeros. If current bitstream byte index greater than or equal to len blah 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 blah, then we will oops. Current bitstream byte equals 0. I'm just gonna try padding it with like 0, 0. Oh, that's not good. Nope, don't do that. Don't do that. Stop, 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 stop. It's like it's just not getting the end of data marker. There we go. That is not a correct decoding, but it's not crashing anymore. 101. Where's our image? 1012. Yeah. That looks correct. So we got 1012, and then we've got a bunch of garbage afterwards. But that is correct for the first few. Like this is definitely like it's correct decoding, but we're still hitting the end, the end of the thing. It's just like a case where things just like go off the rails once it reaches the end of it. I don't know. Oh, wait a minute. So the data that's coming out of that is actually like that is not compressed for those first few bytes like at all. Weird. Make sure it still works for tiny.gif. Yeah, okay, tiny.gif is still functioning. tiny2.gif, you get kind of some weird results. Ooh, that's really wrong. That's really, really wrong. What's loading current bitstream contents? That is set when we call set bitstream. And that is using the like the block byte count that we get immediately before. So there is, oops, not where I wanted that to go. If we look at the okay, so we get this is the table-based image data. We get the LZW minimum code size. That's where we read this thing and print out that. And then we get the data subblocks, and the data subblocks is image data described in Appendix F. The data subblocks have the first byte of it is the size of the block. So if we go down to Appendix F, I think we'll see that. Yeah. So once this is Appendix F right here, block size and then data bytes, and then there's there's a block terminator. The code that terminates the LZW compressed data must appear before the block terminator. Zero length data subblock is used to terminate a sequence of data subblocks. Oh yeah, okay, we already handled that case. Anyway, if we look at the package of the bytes, once the bytes have been created, they're grouped into blocks for outputs by preceding the block, each block of 0 to 255 bytes with the character count byte. So that's what's happening right here. A block with 0 byte count terminates the raster data stream for a given image. And I don't think block bytes. Yeah, block byte count is just 3. I've never heard of that. I don't know what that is that you're referring to. Get bytes, block count. Yeah, so we're getting like these 3 bytes out of it. We're getting 3 bytes, and in those bytes we're getting a whole bunch of individual codes. And in fact, if we get rid of the safety stuff here, let's just get rid of the guardrails, and just do that directly. I think it's still gonna crash. Bam, there, it crashed. It didn't crash, it just, hit an error. Out of bounds get index 3 on base array. Wait a minute. Color value 3 should actually be valid. 0, 1, 2, 3. Yeah, that's... Yeah, we should actually have like a 3 in our current bitstream contents. Why don't we? Do we have to initialize the bitstream contents? No, wait, not that one. Current bitstream contents. Oh, right, no, that's an index into the bytes because we're going past the end of the thing. Right. So again, we got the clear bit. We got 1012, which is the actual image, and then we got a bunch of garbage afterwards. So it's interesting that it's correctly giving me the image data, but it's not giving me any end of block stuff. And there's in fact extra garbage past the end of it. I don't know, pretty weird. I gotta wrap up stream now, so yeah. We'll figure it out. We'll figure it out. Probably. Actually, it looks like I have like, wait, hold on. 1, 2, 3, 4, 5, 6, 7, 8. Got 8 blocks, or 8 bytes. And we actually only need like 5 of them. We're just not ending the search at the right point. Like it just goes past the end of the array, and then it's not garbage data exactly, but like this is it trying to go past the end of the array right here. This down here, I don't understand what this stuff is. This looks like garbage. But these are values that actually got loaded from the GIF, so whatever. Unless we are supposed to change, we might have to change the minimum block size as we go. The output codes are of variable length, starting at code size plus 1 bits per code, up to 12 bits per code. This finds maximum value of blah 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 blah. Whenever the LZW code value would exceed the current code length, the code length is increased by 1. The packing and unpacking of these codes must be altered to reflect the new code length. Okay, but how the hell do we detect that? That's gotta be it though, right? Remember the LZW code value would exceed the... Oh, wait, no, maybe it's when we... No, like, it would be when we add or remove something from the dictionary, but we're not actually doing that yet. So... It's the position of the highest bit in the largest code? Yeah, sure, but how do we tell the difference between that and just it being a bit in the next number over? Because, like, by definition, when we're reading the bits, we're only reading, like, that many bits at a time. So how can we tell if the number is actually supposed to exceed that number of bits? Because we've only read that many bits. And as far as we know, the next number is... the next bit in the bit stream is actually just the start of the next number. Like, how do we tell? Whenever the LZW code value would exceed the current code length is increased by 1. Table shown above is being built of strings of increasing length. The scheme can The scheme can function, but the table consumes an unpredictable amount of memory. Memory can be saved in practice, blah, 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 blah. Shorter code lengths can be used for smaller palettes, blah, 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 blah. Symbol width need not match the palette. Symbols can be any width from 2 to 8. The palette size, blah, 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 blah. Symbol could be, set could be at 8, even if value is 0, 1, blah, 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 blah. Initially contains codes that are one bit longer than the symbol size. In order to accommodate the two special codes, CLR and END, and codes for strings that are added during the process. When the table is full, the code length increases to give space for more strings, up to a maximum of blah, 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 blah. As the decoder builds the table... Wait. Tracks these increases in code length and is able to unpack incoming bytes accordingly. I don't know if this is actually the thing that we're dealing with, but because in order to actually... Oh no, Super Retro Heart! I'm wrapping up stream! Oh no! I'm actually 5 minutes over! Oh no! Thank you for the raid. How'd your stream go? Hack. Were you doing art? You got an art tax? Hang on a second. If we do an art tax, I need to let's see, moderation settings, URL, block hyperlinks unchecked. There we go. Morning art stream? Yeah, art hacks. Let's go. Come on. I want to see. We're trying to make a GIF decoder at the moment. It's going okay. We have a little bit of a mystery with the LZW decompression code, so which is different than the example stuff that we've been given here. Use a bit width, so just grabbing bytes is inadequate. I am not grabbing bytes. Yeah. We're grabbing like a set of bits at a time. The test image looks like this. It is 4 colors, and we're using 3 of them. Yeah, we've already written the code to do a bunch of that stuff. So, yeah, I think there's like the thing that GIF does specifically that LZW doesn't normally do, that changes the size of the code length while it's decompressing, which it's really, really vague about how that works. Also right here. Yeah, it does not make any sense at all. I might have to dig around in some open source code for that or something. Anyway, that's what we're stuck on. We actually are able to decode one GIF, so we can decode this GIF, but we can't decode this GIF. That's kind of where we're at. All right, I do have to wrap up stream though. It is past end of stream time for me. Super Retro Heart. Do you want to show off art for the art tax, or are you out of here? I'm gonna go figure out someone to raid while we're thinking about that. But yeah, unfortunately, you misheard. You know, let's see the art. Come on, I like your art. Okay, hold on. I know who we're gonna raid. All right. Just don't post a GIF, whatever you do. I've seen enough GIF I've seen the inside of this wretched format and vaguely coded spec. Bridgewater has redeemed a I can't leave without my buddy Superfly. It's interesting that we're actually getting the correctly decoded image for this one, and then, but no, like, we're not getting the Terminator. Thanks for stream. Have a great rest of your day. Oh, thank you for being here. Also, we're just supposed to know that it's time to end the stream. Sorry, the bit stream, not the stream. Time to end the bit stream based on the number of pixels we've read. That'd make it harder to split up the things, though. Flash of a light, soft yet bright. I forgot the lyrics again. Alright, now I just have to figure out how to copy it out of here. Oop. Aw, that's really cool. That's super cute. I like this. I like your art. Oop. There we go. That was awesome. Alright. Well, with that, we do have to wrap up stream now. Thank you for sharing your work. I like that. Is that a bomb? That seems dangerous. I love your line art so much. Oh my god. Hold on a second. I'm gonna zoom in. I'm gonna zoom in on your lines. Stop. I'm zooming around all over the place. I like your line art so much. Like, it's so clean and nice, but it's like thick lines too, you know. And I appreciate that. I like that kind of style. Anyway, all right, let's kick off that raid. Soldiers that fall in the rain, all alive in the world today. Won't light up the night into which I walk away. All right, well, thank you everyone for joining me for another weekday morning art/dev stream. Really appreciate having y'all here. You're all awesome and amazing. Hope to see you next time. Take it easy, take care, be kind, show compassion, show empathy. Don't get in a knife fight. And stay safe. Thank you, Stream Stack. It's Stream Burb today, but you're welcome. Go away alone. They don't go alone. Dang it. Why is this compression algorithm so complicated? Why can't things be simple? Yeah, whatever. I'm gonna get Kelly straight up. Alright, to the rest of you, bye! Oh yeah, I forgot the raid message. There you go. There's the raid message. All right, bye. I'll figure it out. Probably.